While we're looking at the behavior of matter, we should make sure we define a few other basic terms that we use a lot in this course. We've already seen some of these before, but now we're going to look at them a little more carefully. First off, we have mass. This is the amount of matter in an object. As we saw in the last chapter, it's not the same thing as weight. Remember that weight is the force you feel from gravity. While weight depends on mass, it also depends on how strong gravity is. If you went to the moon, your weight would be a lot less because the moon has weaker gravity than Earth. But your mass would be the same as it is here. You'd still be made of the same stuff. The standard units of mass are grams and kilograms. Next up is volume. This is the amount of space something takes up. This may or may not be related to mass. After all, consider a beach ball. It has lots of volume, but very little mass. There are several volume units, including cubic centimeters, cubic meters, liters, and gallons. We don't often need specific measurements for volume in this class, but when we do, we'll mainly use cubic centimeters. The last one, and possibly the most interesting, is density. Density is simply defined as the mass divided by the volume. It commonly has units of either grams per cubic centimeter or kilograms per cubic meter. Mainly we'll use the first one. We'll look at density more on the next slide. I just said that density is an interesting property, and the reason for this is that density is an intrinsic property of the materials. What this means is that it doesn't matter how much of a material you've got. In a given set of conditions, it will always have the same density. For example, a glass of water and a lake both have the same density. This will change if you change the temperature or pressure a lot, but if you know the conditions, then you know the density a material will have. Here are some common values for density. Common rocks have densities of 2 to 4 grams per cubic centimeter. Liquid water has a density of about 1 gram per cubic centimeter. That's a good easy number to remember. The air around us has a density of about 0.001 grams per cubic centimeter, 1,000 times less than water. So think about what this implies for astronomy. When we look at a planet or star, it's often hard to tell what the inside is made of. However, if you can figure out the density, then you can get a pretty good idea of what it's made of simply by looking at common materials with matching density. Think about how you would measure the density of an object. You need to measure the volume, which you can get from the size. You can see this and measure it fairly directly. You also need to figure out the mass. If you don't remember how to do this, go back to the last chapter and look over the notes on orbits to see how we measure masses in astronomy. When we do this for planets, we can get some surprising results. For example, we find that the density of Saturn is only 0.7 grams per cubic centimeter. That means it's less dense than water, and it certainly isn't made of rock like the Earth. Finally, if the density in an object is changing, that tells you that either its composition is changing or that the conditions like temperature and pressure are changing. Remember that density is mass divided by volume. In astronomy, many of the objects we're studying are either spherical or close to it. So to find their volume, we can use the formula for calculating the volume of a sphere. This is V equals 4 pi times r cubed divided by 3, where r is the radius of the sphere. The main trick here is to make sure that you've got the right units, or you'll get an answer that doesn't make any sense. The density units that are used most often are grams per cubic centimeter. As we saw earlier, the density of water is 1 gram per cubic centimeter. So far, we've been working with kilograms and meters rather than grams and centimeters. So what I'll do is show you how to calculate the density in kilograms per cubic meter. Then, when we get to the end, I'll show you how to convert that to grams per cubic centimeter. Let's try calculating the density of a planet using its mass and radius. We'll do this for the planet Saturn. we'll take a lot of small steps, starting with the equations we just saw. Once again, density is mass divided by volume, and the volume of a sphere is given by V equals 4 pi r cubed divided by 3. Saturn is a big planet. Its mass is 95 Earth masses, and the radius is 9 Earth radii. Now let's do the unit conversions. We'll start with Saturn's mass. Remember that 1 Earth mass is 6 times 10 to the 24th kilograms. Since Saturn is 95 Earth masses, it's 95 times as big. So Saturn's mass is 95 times 6 times 10 to the 24th kilograms, which is 5.7 times 10 to the 26th kilograms. Notice that since we multiplied the Earth's mass by almost 100, the exponent went up by 2. This is a good point to stop and see if your answer makes sense. Remember that a kilogram is very small compared to a planet. Your mass is probably tens to over 100 kilograms. Saturn is a big planet, so there should be a huge number of kilograms in it, and 10 to the 26th fits that. We've taken care of the mass units. Now let's look at the radius. We also need to convert Saturn's radius from Earth radii to meters. We know that 1 Earth radius is 6.4 times 10 to the 6th meters. So 9 Earth radii is 9 times 6.4 times 10 to the 6th meters, or 5.76 times 10 to the 7th meters. Once again, check to see that the number makes sense. A meter is a very human scale. Most adults are between 1 and 2 meters tall. So from the core of a big planet to its outer edge should be a lot of meters. The number we've got, which is almost 60 million meters, makes sense for this. We've got all our units set. Now let's find the volume of Saturn. We start with the volume equation we've already seen. Then we write it all down again, but this time with the value of the radius filled in. Notice that I've included the units. In the next step, we'll cube the radius. Notice that the units get cubed as well. The radius cubed is 1.91 times 10 to the 23rd meters cubed. I've also calculated the 4 pi over 3. This gives roughly 4.19. Since these numbers are always the same, you'll always get 4.19 for this step. That can save you some time if you do this calculation more than once. Then we do the last multiplication and find that the volume of Saturn is 8 times 10 to the 23rd meters cubed. Once again, we expect a very big number here. It is the total volume of the planet measured in very small units. In case you're tempted to find the volume first and then convert to meters, I recommend that you not do it that way unless you're very careful. Once you're working in cubic units, the conversion factors are different. So if you just use the same conversions we did here, you will get the wrong answer. Now that we know both the mass and the volume of the planet in the right units, we can go ahead and find the density. We write down the density formula. Then we write it down again with the values we found for the mass and the volume. Notice that what we've got is two huge numbers divided by each other. In fact, they are almost the same size. So when they divide, you'll get an answer that is actually quite small. The answer we get in this case is that Saturn's density is 710 kilograms per cubic meter. However, we said we wanted this number in grams per cubic centimeter. To get this, we need to divide the answer by 1,000. That's the conversion factor between the two sets of units. When we do this, we find that the density of Saturn is just 0.71 grams per cubic centimeter. If you compare this to the sample densities listed a few slides ago, you see that Saturn's density is less than the density of water. As we said earlier, Saturn is a very low density world. In general, objects in the solar system have densities greater than 0.1 grams per cubic centimeter and less than 10 grams per cubic centimeter. In our solar system, the densest planet is Earth, with a density between 5 and 6 grams per cubic centimeter. The least dense planet is Saturn. Now you should try to calculate the density of a planet from its mass and radius. Remember to be careful with the units.